Okay, so we are live. Hello everyone, welcome back for LLM Bootcamp 0 to Hero in LLMs. So we will be starting with the week 3 for pre-trained models transformers. In week 3, module 5 is so week 3 module 5 is more about BERT and RoBERTa transformer models, and we have Saurav Maheshkar who will share his expertise on how you can get started with these models. So without further ado, we'll let Saurav start with the session. But initially, still before people join in, can you talk about how you got started with your ML journey and where do you work as and all those things?
Sure. Thank you, Tarun, for the invitation. This is one of the few opportunities I get to speak about LLMs outside of work, so it's always nice. Um, I started in machine learning as a technical writer first. So I used to write blog posts for this company called Weights and Biases. That's where quite a few of the deep learning people in India have come from. But yeah, I started writing blog posts for Weights and Biases, I think 2 years ago now. I started in January 2021. I wrote articles for I think 6, 7 months, and then as soon as I was finished with school, they offered me a full-time role at Weights and Biases on the growth team to work as a machine learning engineer. So yeah, that was my first full-time job. I stayed there for uh, almost 1.5 years. I have since left and joined. Well, I also worked as a software engineer for the University of Manchester, and currently I am at Recourse, where I work on the research team. But yeah, that is how I got started with machine learning.
Yeah, good. So I guess we'll start with the session. And before we start with week 3, I just want to say that module 5, which is BERT and RoBERTa content, is already available on our website. And we'll have module 6 live session tomorrow at 5:30 p.m. And yeah, we'll start with the session.
Hmm. Okay, yes, let's get started. Uh, Again, this is a slightly longer introduction. So, hi everyone, my name is Saurav Maheshkar. I am based out of Manchester. I work at this small startup called Recourse, where I'm on the research team. I work with LLMs in my day job as well. My job is to improve conversational agents by grounding them with information from medical knowledge bases. Overall, I'm interested in geometric and representation learning. I also do Kaggle, or at least used to do. I'm not that frequent anymore, but yeah, I also love open source and I drink coffee a lot. Okay, so yeah, let's get started. The outline is simple enough. We'll first go over BERT, then we'll have some sort of a code walkthrough. We'll go over RoBERTa, have a code walkthrough for that as well, and in the end, we'll take questions. Um, okay, yes. So the BERT paper originally came out of Google research. Um, it was one of the most sort of fundamental papers when it comes to transformers and self-attention as well. And it aimed to tackle the problem of models being left to right biased. What does that mean? Let's go over that. So on your screen, you'll see two of some of the popular LLM models from back in the day, GPT from OpenAI and Elmo. And as you can see, they look quite similar to LSTMs. One of them even use LSTMs as a subunit. But essentially, you have these encoder tokens, which are the E's, and the target tokens, which are the T's. And in any attention block, you sort of combine them together in various manners, right? But if you look at GPT, right, and you look at the smaller, the blue rectangle, you'll see that we only sort of take in the information from the left hand side of it. Now, that might seem natural to us, right? Because sentences have a sort of left to right bias, right? words which are in the end of the statement carry context from the start. While that works, it is an inherent bias in most of our systems, and therefore, back then we were not able to extract a lot of information from it. Now, while GPT works great, right? We have all used OpenAI, ChatGPT, or Google Bard, perhaps, but still, like, this is some bias which we would like to get rid of, right? Because there can be instances where a word which is in the middle has context from the right of it as well, right? So to sort of mitigate this bias, Elmo came up with a possible solution, which is to use two subnetworks to learn left to right representations and right to left representations as well, right? So you sort of disentangle the task to make sure that, okay, you are learning some sort of right to left context as well. But the way that they mix those representations together was not really smart, right? So as you can see, the same tokens are being passed to the two networks. You learn two separated representations and then just simply concatenate them together, right? This is not joint learning. This is separate left to right and separate right to left representations being learned, but just being added. What we really want is to make sure that we learn both of these representations together in a coherent manner. That's the problem which BERT aimed to solve, and it solved it quite well. now most of the most of the transformers nowadays have bidirectional embeddings. So when I say bidirectional, I mean embeddings are being learned both from left to right and right to left, right? So just to summarize it up, we have an issue called the left to right sort of bias. GPT, which is sort of based on the more traditional transformer architecture, doesn't allow us to learn in the other direction. Uh, so the way it works is, for a word which is towards the end of the sentence, you only have aggregated embeddings from the previous part of it. Whereas we have things like Elmo, right, which were sort of a popular approach to create word representations, and they did try to mitigate this issue. They did it by training two separate LSTMs, but then simply concatenating them together. But again, these are two separate networks. You don't really have like a coherent form of learning. So now this is where BERT comes in. BERT has two key contributions, one of them being bidirectional learning and one of them being the new pre-training objective. We'll go over the bidirectional aspect right now. So here we can see the comparison between BERT, GPT, and Elmo. As you can see, BERT and GPT look very similar. It's just that every intermediate representation is linked to every other, right? So if you look at, let's say, the row which has T2 and E2, right? We have context from the end of the statement as well. So it's a relatively simple implementation, but it enables us to learn in both directions. Right now, implementations wise, it was a bit difficult to get started with, because with the left to right training problem, right, you had an inherent structure to your data. The model understood that, okay, it's supposed to start from the left and it's supposed to end there. With bidirectional learning, we had to come up with new ingenious ways to tell the model to sort of stop, right, or this is a start. The way the BERT authors did it is by using special tokens called the class tokens, the separator tokens, and so on. Nowadays, we have lots of these special tokens, but yeah, it's a very simple approach when it comes to it. Right? Now, let's have a look at like the other key contribution of the paper, and to do that, let's zoom back out, right? One of the reasons that language models are so good in what they do is because of this thing called pre-training, right? So we sort of train the model twice. Once is we pre-train them and then you fine-tune them. The reason we split this, right? While pre-training, we help the model gain an understanding of the language itself. Right, we're not training for a particular task. We just want the model to understand what it's going to be working with. Right, it works in vision as well. This is the whole concept where transfer learning comes from. Right, you first establish a base, and then you can train either like a smaller model or all of the model on your particular task. Right, so we have pre-training, we have fine-tuning and evaluation. One of the major contributions of BERT was the new pre-training paradigm. Now, this pre-training paradigm which BERT introduced is what most modern large language models use itself. It is largely inspired from the field of self-supervised representation learning, where you train using unlabeled data. Earlier, what people used to do is we used to do next token prediction or next sentence prediction. So essentially, given a statement, what is at the end of it? So it was a labeled data set. But what BERT introduced, the new paradigm of masked language modeling, allows us to bypass all of that and just train using unlabeled data, which is really good because labeling data is very expensive. Okay, so now let's think about how we used to do things earlier. Right, we used to have sort of the next word issue. Now, so let's say we have x0 till x3. Earlier, our task used to be to tell what x4 was. Right, so it is a simple prediction task. And as you can see, it is obviously inherently left to right biased, right? X4 has aggregated information from X0 to X3, but let's say if we consider X2, there is no information coming from the right of it, right? What instead the authors of BERT proposed was to do this thing called masked language modeling. Now, a simple example is what you can see on the screen. The man went to the masked store. Now, mask can be, for instance, the most obvious example which comes to my mind is the man went to the grocery store. But this is a very simple thing to implement, right? So randomly for any given sentence, just mask out one particular word and train your model to predict what it is. Now, this word can be in the middle, it can be in the start, it can be in the end, right? So like during the whole pre-training procedure, the model is forced to learn representations from both directions, right? This is sort of like a better way to understand things. So this figure is taken from a blog post called "Self-Supervised Learning: the Dark Matter of Artificial Intelligence." But if we sort of think of our data as like a rectangle, right, which is filled with some sort of this green fluid, then masked language modeling can be understood as you take out chunks of it, right? You leave one part blank and then you leave the rest of it in, and then you train the model to fill that space in again. Now, masked language models is the most common paradigm of large language models which you will encounter in today's world, right? And it is a pre-training objective. The task is simple enough, right? So you randomly mask some of the tokens, and the objective is to tell what the masked word is. But you only do it with reference to the current context, right? So it's sort of like you train the model to fill in the blanks, but you create the blanks yourself randomly, right? Now, this obviously allows the model to learn in both directions, and therefore it allows us to train a bidirectional transformer, which is what BERT is, right? It is a pre-training objective for bidirectional transformers. Now, once again, to summarize, the key contributions of BERT were making sure it's bidirectional and this new pre-training masked language modeling paradigm, right? Here we can see what BERT essentially looks like while training. So you have pre-training and fine-tuning. You have a unlabeled sentence pair. So towards the left, you'll see an unlabeled sentence pair where you mask out some bits of it. Again, you'll see separate sentences A and B because the model is trained to fill in the mask using the context being the sentence itself, right? So it forces the model to stay local, but then again, learn bidirectional uh, embeddings. And then once you have pre-trained the model on this general task, which is to just understand what the language is, what our vocabulary is, then you can fine tune on whatever task you want, right? On the end, you can see squad, which is a question answering data set. You can see NER, which is named entity recognition, and other variants. But yeah. Some resources and examples to get started with. The BERT paper is very easily readable. It has a relatively fewer jargon when it comes to AI papers, so I definitely recommend you read it. Google Research has their official implementation on BERT, which is also very readable. It is small; you don't have to know about what the various subclasses are. And then there's a great explanatory video by Yannick Kilcher as well. So that's BERT done. Now let's think about RoBERTa, right? Now RoBERTa it essentially was like a hyperparameter study done on BERT. And what the authors concluded is, so RoBERTa came out, I think, 9 months after BERT did, during which like a lot of other models were also proposed. Now, what the authors of BERT said, and BERT is a relatively smaller model, folks. It is an extremely small model. Yes, I think it's fair to say it's an extremely small model in today's age. But yeah, what the authors of the paper claimed is that if you train BERT using enough data, using sort of these smart engineering training tricks that we have observed, it is either at par or better than the other models in the field. Right. So it's essentially the same architecture. So think about bidirectional embeddings, and then think about this mass language modeling concept, right? So it's just that, but we are improving on top of it using things which we have learned from training, like lots of BERT models. So it essentially was a replication study. This is the word that they used in the paper as well, and they pre-trained tons of BERT, and then noted the effect of various hyperparameters on their eventual performance, right? And the training data set size as well. Now, this might seem obvious to you, like if you use more data and train bigger models, you'll get better performance, but that usually doesn't work. Scaling laws says that it works, but that's sort of for pre-trained and fine-tuned models, right? But if your final data set which you are evaluating on has, I don't know, let's say 15,000 examples, then scaling up is not the solution. So while it works in like an academic sense and it makes obvious sense, is not that simple. So one of the questions that they asked was static versus dynamic masking. So the implementation of mass language modeling, which the authors of BERT came up with, was static. As in, the way you create the data set is you create masks beforehand, right? You augment your data set to have masks and then feed it into the model. What the authors of RoBERTa questioned is, do we need to do that beforehand, or can we do that on the fly as well? Right? You consume the data set as it is, but while you are processing every statement, what if we then introduce masking? Right? And as you can see, there are some marginal improvements when it comes to, for instance, squad when you see 78.7 or SST when it's 92.9. It's low on MNLI, but then again, they run like a bunch of experiments. So these small sort of improvements eventually compound. Right. So based on their experiments, dynamic masking works better than static masking. Now, this is a computational overhead because, as you can imagine, it's an extra step which is being done before the data is fed into the model itself. So it adds some sort of extra computation time. It might depend on like how long your sequences are, how much memory you have left on your accelerators. But again, based on their uh, evaluation, it works better. Whereas like static masking is something which is relatively simple because you can run sort of like a cron job, which is like as soon as you have your data set, you augment it beforehand before feeding it into your model. So you do save some time and memory, but based on their experiments, the dynamic masking of RoBERTa is better. The other question which they asked is, do we actually need next statement prediction or not? Now, although like the key contribution of BERT was mass language modeling, they did also use next statement prediction, which simply said is given a statement, what comes after it, right? So there is still that task, which sort of still has the left to right bias, but the authors of BERT did use the NSP task as well. Now, the authors of RoBERTa question, do we actually need the NSP task or not? Right. And according to their results, you don't actually need it. It adds like one of the conclusions which you can draw from it is that it also adds left to right bias. So based on their experiments, if you don't use it, it's actually better. As we can see, without NSP loss, the performance is better on almost all data sets, except again at par in MNLI. But as I said, like these improvements compound over time, and that's what makes RoBERTa like a better model when it comes to BERT. Another thing which the authors observed was bigger batch sizes work. Now, these like seem very easy conclusions now. Just train bigger, go larger, train more, and it works. Uh, but again, there is some sort of like a trade-off there. Most people can't train with batch sizes of 8,000, 2,000, whatever, right? So there is a trade-off there. And like, as you can see, with a batch size of 2,000 and having like 125,000 steps over your data set, the performance is optimal. And as you can see, scaling up doesn't actually work. If you use a batch size of 8,000, which is the last row, the performance actually goes down. The best performance is observed when there is a trade-off there. But yeah, one possible reason why this result exists is if you have a big enough batch size, you can actually learn useful representations from both directions. Whereas if the statement is relatively smaller, it is hard to learn representations from both directions, right? Yeah, so that's another thing that they experimented with. Then there's of course more data. Right. So if you pre-train using larger data sets, what impact does it have when you fine-tune them? Again, now let's think back to that figure, right? You have pre-training, you have fine-tuning and evaluation. We are increasing the data set of a pre-training and then observing what effects it has on evaluation, right? So it's not a pre-training metric, it's a final evaluation metric. But yeah, what they observe is that yes, if you use more data and if you train for longer, right? That's so RoBERTa with books and wiki. These are two other data sets which the authors released with the paper. So that is 16 gigabytes. If you train like a BERT large with books and wiki, that's still 13 gigabytes. But yeah, if you train using more data, the performance is better. As we can see, a BERT large has 90.9 performance on Squad 1.1, whereas like a RoBERTa on the same data set has like 93.6. So if you train using sort of more data, it works better. If you add additional uh, data, so if you go from 16 gigabyte to 160, that's obviously more. That's 10 times more. There is, well, a marginal improvement, but yeah. And if you pre-train longer, even longer, the performance improves. Now, although scaling laws say that like the bigger the better, as you can see, with like 10 times more data, you have a marginal improvement of 1 when it comes to squad, right? So there is that question as well. Like if we scale, our metric might increase, but will it be worth it? Are you willing to like spend lots more on compute, but have just marginal improvements of, let's say, 1 or maybe 2? Right. But yeah. Um, Again, the RoBERTa paper is very easily readable as well. These fundamental papers have relatively less jargon. So if you want to catch up to large language models, while it is very exciting to use new tools and learn about new models, the papers are relatively harder to read. So I would always recommend you go back and read sort of these fundamental papers. But yeah, the official code is there on the Facebook Research's Fair Sequence repository. Again, the code is very readable. They have broken down, they have uh, broken it down into chunks. And Yannick Kilcher again has a great explanatory video about this. Now, large language models are famous because you can pre-train huge models and upload them for free, and then you can fine tune on smaller data sets. The Hugging Face Hub has a lot of BERT models. As you can see on the right hand side, I just searched BERT yesterday, and there are 16,602 pre-trained models available for you to use. You just it's very simple to use them, and there are a ton of variants available. You can find models which are pre-trained on different languages, different sort of data sets. It's not even like a general data set, right? You can find models which are pre-trained on medical information, on I don't know, just Shakespearean texts and whatnot. Now, how do you load them? It is very simple. So you just you go to transformers, import their auto tokenizer and auto model class, and then just use them. As you can see, it says auto model for masked LM, which is an automatic model for masked language modeling. They have sort of these other classes as well, but you'll see we have different tokenizers when it comes to each of these different model as well, right? Because they use different sort of tokenization strategies, and both of them are quite important. You can't use a different tokenizer and a different model. They have to be the same because the model has been pre-trained to uh, understand the data which is fed from like its particular tokenizer. Now these now you see we have BERT based uncased as an example, but then again you can use any of these models and it'll be good. Now, before we actually go on to the example notebook and see some code, are there any questions?
Yeah, hi sir. Okay, so there are two questions, I guess.
Mm-hmm.
So the first is, I think the major contribution of Elmo was that NLP model can be trained and fine-tuned and re-fine-tuned, like in case of CNN models.
Yes, fair enough. That is a good enough conclusion to draw from the Elmo paper. And yes, they can be fine-tuned and re-fine-tuned, like in the case of CNNs. But then again, Elmo was like relatively a bit more expensive because again, the model contains two subnetworks that you have to train. So the usability of it has, well, it has not stood the test of time. But yeah, that is a good statement.
Uh, the next question is when to use
Oh,
BERT or RoBERTa.
okay, good question. Sadly, the answer is it depends. It it depends on what your final evaluation metric in. It depends on what your data distribution looks like. My advice would be just experiment with both. For instance, whenever there's a new Kaggle competition and I don't know which model to use, I just try out all of them. Again, not all of them. Like you just try out the fundamentals, right? You try out a distilled BERT, you try out a BERT, you try out a RoBERTa, maybe a DeBERTa. But yeah, there is no concrete answer. Now, I would always recommend to use sort of like the more robustly trained model, which sadly happen to be bigger almost always. But yeah, there is no concrete answer when it comes to that. It's just always it depends. Yeah.
Yeah, I guess we can go on with the notebook part.
Okay. Um. Okay. Share my screen again. Then present. Are we on the notebook now?
Uh, yeah,
Yes.
we can proceed.
Okay. Okay. Yes. So this notebook is just modified from a Keras.io example. Original credits to the authors, but yeah. So we'll use the transformers library as we discussed previously, and we'll use them to sort of install the data sets as well. So let's simply run that. Again, this notebook is available online on keras.io or my GitHub gists page. But yeah, there is sort of these parameters which we need to consider, which is the maximum length of the sequence that we feed into the model and the document stride as well. So that is how frequently do two parts of the context overlap. But yeah, these are sort of pre-processing steps which we need to take care of. Now, again, we are working with sort of a mass language modeling objective, and when I say processing, we are doing sort of static masking, as you'll see. Um, okay, so now while our libraries are being installed, we can look over how easy it is to just install datasets.
Hello, Saurabh.
Yep.
Hello. Yeah, can you zoom your screen?
Okay.
Yeah, thank you.
Okay. Yeah, great.
Yeah.
Okay. So our libraries are installed, so we can get started. So now the datasets library by Hugging Face has like a very simple function, which is just load dataset and you put in squad. In this notebook, we are concerned with like question answering. But yeah, it's simple enough if you have like other data sets as well, and like you can borrow code from their own examples repository as well. A point to be said, we are working with GPUs at the moment. As you can see, we are connected to a T4 instance right here with sort of, I think, 80 gigabytes of virtual memory GPU. Sorry, no, 14 gigabytes. Yeah. Again, let's see our example. So there is a ID, then there's the title, and then there's the context, right? The context is a lot, and then based on this context, you will have a question answer pair. Now, as you can see, this statement is something about, let's see, I think it's related to architecture somehow. It's describing a statue or a building. And then you have a question which is to whom did the Virgin Mary allegedly appear in 1858 in Lord of France? So it's like a history thing. And then you have answers, right? She apparently came to see Saint Bernard, and where does the answer start from within the context, right? So this is how our data set looks like. So given a context, we have a question answer pair, and you can think about context as being like an example statement from which you are having a question and answer. This is sort of like text comprehension like we had in school. And then you use the auto tokenizer. In this example, we'll use DistilBERT, but as you'll see, even for DistilBERT training on a GPU takes quite a bit of time. We use the official checkpoint available on the Hugging Face repository, and we create a tokenizer from it. This will sort of download the file and then set up the tokenizer. Now let's have a look at the pre-processing steps. So sort of L strip is you remove left space from the question itself. So it might be the case that the way that the data set is made, it might have sort of an extra space which you sort of need to get rid of. Same for the context as well. And then you tokenize it, right? You tokenize the question, you tokenize the context, and then we sort of use the max length and the document stride hyperparameter which we had specified above. And sort of these steps are to ensure that every example corresponds to one single feature. And then we label them using the start positions and end positions. Again, this is like a question answering specific pre-processing step, but essentially you tell, okay, where does the answer start from, where does it end? So this just does that. This class token ID is something which is specific to BERT, which is like a CLS token. That's the way like BERT recognizes different classes. Yeah, sort of these pre-processing steps are not that sort of, again, this is question answering specific, so we'll like skip over these, but essentially what it does is that it creates question answer pairs, it tokenizes them, it featureizes them, ready for the BERT model to ingest. So you just sort of map this function across the whole data set. Now this will take a bit of time, and while that is happening, we can go on to the other steps. Ooh, prepare train feature. Oh, we did not run this. Yep, there we go. So while that is running, we can look at how simple it is to create a model as well. Now, Transformers has like a lot of auto model classes. In the slides you saw auto model for mass language modeling. Here we are using them for question answering. So you just use that auto model class, and it's as simple as class from pre-trained and then the checkpoint. In our case, this is DistilBERT, as we specified above. But yeah, again, we use TensorFlow. It's very simple to use. PyTorch as well. Just TensorFlow makes for shorter, concise code. That's why I've specified that in the notebook. But yeah, you create like a normal optimizer. You use mixed float. This is something which Keras allows you to do. Mixed float leads to better performance, but it is a bit training intensive. And as you'll see, like we are pre-processing the data set at the moment. And again, we should notice Squad is a relatively big data set. So while we were able to ingest it quickly enough, the actual training might take a bit of time. As you can see, DistilBERT, although a relatively small model, as we'll observe soon enough, takes a lot of time to train. Now, model.fit, again, just for one epoch, I think if you want to fully train the model, it would take around, I don't know, an hour. Yep, it will take like 50, 60 minutes in order to train the whole thing. We'll obviously not train the whole thing right now. But yeah. And then again, there is inference code for you to play with as well. So you provide the model a context, again, this is taken from keras.io example. So, it's the description of keras, and then you ask the model question, what is keras? And then, it will give out an answer for you. But yeah, there are lots of things to play with here. You can simply change the model checkpoint to point to something else. You can point it to RoBERTa, you can point it to BERT. A T4 is big enough to accommodate models up to, I think, a DeBerta large if you use like engineering tricks. But yeah, lots of things to play with here. But then again, we're just training for one epoch, right? You can train for longer, but that is something you can't do on a coil app. It's gonna take you lots of time. But yeah, so that was the notebook. Okay, then again, any other questions?
Yeah. So there is one question: what is the difference between NLP and CI?
What is CI here? I don't think I understand the context. Tarun, do you know what he's referring to?
Uh, I am just wondering whether it is CI or CV.
Ah, okay, good.
Mohan,
Yeah,
do you want to specify what is CI? Until he replies, we'll take the next question.
yep.
I just went through the paper. That paper, what does glue specify?
So it's a metric. It's what we use to evaluate models. Um, yeah, it's just like a specific metric for a specific task. It's just a
If
benchmark
I'm
metric.
not wrong, I guess glue is nothing but it is a combination of 9 data set. When I
Oh,
was
okay, you mean the
studying,
glue benchmark. Okay, sorry. Yeah,
yeah, yeah.
yeah. Okay, yeah.
So if you look at the paper, right, I don't remember for the bird, but Robota has specified this. For glue, it is the combination of 9 data set, and for the benchmark, what they did was BERT and Robota. They'll take the average of all the data set. So it's a metric parameter to evaluate your text-based data set or text-based LLM models to be specific. Uh, there is no follow-up question on CI. Okay. So you have any best practices to share when it comes to BERT and Robota?
Again, I would sort of recommend training a bunch of models and then seeing what the results are. But like if you want to fit and train for even bigger models, there are tricks which you can use. You can use things like uh, gradient accumulation, which is you don't update your model after every step. You hold on to the changes for a while and like do it after every 100 step, after a 50 steps. And like that enables you to train bigger models. You can use smaller batch sizes. CI means conversational interface. Okay. Um, I'm gonna assume by conversational interface again. It's an assumption. Please correct me if I'm wrong. But like, sort of, what I'm assuming is that we have chat windows, right? And that is sort of an interface between us and the model. Is that what conversational interface is? But like from what I gather, is sort of NLP is like an overall field, right? It's the study how you process natural language. It contains like understanding, inference, sort of training, context. It has like a bunch of things. It's like a whole big field. It has different tasks and whatnot. And conversational interface seems to be like a very particular niche. So my guess is like it comes within NLP. But then again, that is assuming conversational interfaces like the chat windows. But yeah, I've never heard that phrase before. Actually, I'll search about it.
Okay. So in your slides, there was also related to fine tuning of BERT model. So,
Mhm.
related to fine tuning, what difference does it make before and after? If we take
Okay.
the large language models, like I won't take the context of Llama 2 and all those things during this conversation, but I'll keep it within BERT and RoBERTa. So, how does it affect the performance for the small models? Because if you look at BERT and RoBERTa, it's not very large models. So, how does fine tuning affect these small models?
Um, Again, fine tuning allows you to tune your model for particular tasks. And like fine tuning is important because you want to use your model for something, right? If you just use like a pre-trained model, and if it was trained using masked language modeling, it only knows how to like fill in masks, right? So if you go to Hugging Face and you interact with any of these models, you'll see that they have pre-trained models for mask filling, and when you use that, you are actually using pre-trained models. But if you see bot models for question answering, they are sort of fine-tuned to perform only question answering instead. So it depends on like what tasks you want to use them for. But yeah, most generally speaking, fine-tuning does improve performance in almost every model, in almost every scenario. So because then again, just look at it as like you're training the model more, right? The more you train the model, the more you can get from it. But yeah.
Do we have any other question? And yes, all okay. We have a question. Do you have any recommendation about the F1 score that is good enough for a model to be used or implemented while using BERT or RoBERTa for few shot learning?
Ooh, good enough F1 score. No, I think it's a very set specific question. So in papers, you'll see F1 scores which are very high. But for instance, I think in most industries, like it depends from people to people. I once chatted with a startup founder who was using a model with an F1 score of zero point 0.6 in production, and it worked good enough for him. But in papers, you'll see performances which are way better. So there is no sort of like a particular number when it comes to F1 score. So while metrics are aside, right? Metrics are a way to like quantitatively assess your model, but I personally recommend you always sort of qualitatively assess the model as well. So like try and interact with it, do some A/B tests, see if like see if its outputs actually make sense. But yeah.
We have one more question. Which lightweight
Mhm.
LLM used for large natural language to SQL?
So I'm assuming this is like a code generation task. So like you give it a context and you want it to output SQL. Which lightweight model? Again, so the way these sort of BERT and RoBERTa was made is like they were biased towards text, so English or languages, whereas like code is something quite different. My recommendation would be to use like distilled versions of code models. So Codex, Copilot, Hugging Face has their own. I think it's called Open Coder or something. But yeah, just use distilled and quantized models of specific like pre-trained code transformers. If you use something as like if you compare a distilled BERT and then a distilled version of a code model, the code model will obviously perform better. So yeah, use any like highly distilled version of Codex or something.
One such LLM will be Star Coder, which you can experiment.
Star Coder.
Any other questions before we wind up this session? And yes, whatever Saurabh had mentioned during this entire session, we'll have the notebook and as well as slides, which will be shared to every one of them. And we will have module 6, which is T5 and GPT, pre-trained transformer models live session tomorrow at 5:30. Uh, any other questions? We'll wait for 1 minute before we have any
Mm-hmm.
question. I guess there are no more questions. Yeah, thank you, Saurabh. Thank you for. Okay, we have.
Okay.
What is the best way to train to produce sentence generation with example input sentences?
What is the best way to train to produce?
I
I'm
guess
assuming you're asking. Okay. Tarun, please go ahead.
it's like text generation, I guess.
Okay. There are pre-processing tricks and things which you can see on the Hugging Face repository. I think they have a specific folder when it comes to text generation. But yeah, I would just recommend to go and see their examples every time you want to like start with something. So Hugging Face Transformers repository, they have a examples folder with notebooks, scripts, whatever. Yeah, go to them always.
Yeah, one more question was only kindly share code so we can play with it. I've
Okay.
added the link where we'll have the content, aiplanet.com bootcamps/LLM bootcamp. So we'll have all the modules, content, and notebooks that will be uploaded at this website. Yeah, Soro, we can share your LinkedIn profile so that if we have any other questions, we'll directly reach out to you.
Uh, yes, my LinkedIn is mentioned in the slides as well. Just Google my name. It's a unique enough surname. I shall pop up. But yeah, it's linkedin.com/Sauramashkar. First name, last name also. But yeah. But I recommend like if anyone has any other questions, please reach out to me via either email or Twitter. Might not be that active on LinkedIn. But yeah.
I'll just, yeah.
Yep.
Yeah, thanks. Thanks again for joining this session, and we'll see you tomorrow. Thank you, Saurav.
Yep. Bye folks. Thank you.